Hello, everyone. In this lesson, we are going to look at transformations and why we use the transformation method to plot graphs. So the first question students might have is why use the transformation method? Well, the main reason is because the usual way to plot a graph isn't the best way depending on the types of transformations that are happening. Usually what we'll do is we will choose a bunch of x values and substitute them into the given equation for the function or relation. That'll give us the corresponding y values. We'll set up a table of values, and then we'll plot all of those points. But the problem with that is that when there are more complicated transformations, so let's say the graph is being compressed horizontally, shifted left or right, and specifically for the x transformations, it might be difficult to figure out what x values to use. Because if the graph is shifted to the left by 15 points or 15 steps, and then is compressed by a certain amount or stretched by a certain amount, well, how far to the left do we have to choose our x values to start in the table of values to be able to actually see what's going on the graph? You might try choosing some x values and notice that you won't get your entire graph because some of it is going to be beyond the points that you've chosen. So the technique of choosing x values and subbing into the equation starts to break down the more complicated the graphs are. So that's why the transformation method is used. And to reintroduce you to the transformation method, depending on whether you've seen it or not, and you should have seen it if you've taken a grade 10 math class, we're going to start by looking at just a generic graph, a graph that doesn't actually have an equation. We're going to take a look at what the parent function's table of values are, and then we're going to do the transformations that are listed with those parent function table of values. So here is the generic graph that I want to use. This is what we're going to call our parent function. This is the starting function. And we want to choose some clean points to use and the minimum amount of points that we would need to actually be able to graph this with the transformations. So if you look here, you can see that there are some nice clean points that kind of delineate where this function, which I've called g of x, exists. So if we look at the coordinates here, it looks like at -14, we have -2 for our y value. At -6, we have 3 as our y value, 0 and -6, 6 and 0, and then 13 and -7. And you would start there for any function or relation that you were trying to do the transformations of. You'd start with the parent graph and then go from there. So if we move to the next slide at this point, you will see that I have listed a transformation that we would like to do to this graph. And that transformation is right here. Y is equal to g of x plus 4. So basically this is saying take the g of x graph, which is the original graph that you see on the screen, and adjust it with the plus 4 using the proper technique. Well, we know from the general equation of a transformation, which looks something like this, that the 4 is in the D position, and that D is a value that would affect the overall behavior of the Y values. It is a vertical translation, and in this case, it's going up by 4. So it is a very simple transformation to do to all of the Y values. We're just going to add 4 to all of the parent Y values, which would have the exact same effect of substituting an x value into a formula and then adding 4 to it. But we're not worried about what the formula is. In fact, we don't have a formula for this. It's just a generic graph, but it's going to behave the exact same way. So all of our y values are going to move up by 4. So 1, 2, 3, 4. So this y value will move up to here. This y value will move up to here. This y value will move up to here. This one to here. And this one to here. And then we can just plot that new graph with as straight of lines as we possibly can, matching the original shape of the first graph. And that is our vertical translation. In grade 10, you would have done vertical translations to quadratics, and you can see here that it behaves the exact same way with just this generic graph. This is another example of a vertical translation. This one is a subtraction by 3, which means that the graph is going to move down. So all of our y values are going to move down by 3. Now you can actually calculate these values if you need them. Sometimes it's easier to use the new coordinates that you would be using. But because the original graph is given, it's very easy to count down by 3. So negative 14 and negative 5, well, if we go to the negative 14 point, which is here, down by 3, we'll now put it at negative 5. So you could plot it using that as well. So that point's pretty easy to see. 0, negative 9. 1, 2, 3 down. 1, 2, 3 down. And 1, 2, 3 down. So our new graph has moved down by 3. And you're showing the transformations in the table of values where they're affecting that particular value. In a case like this, the transformation is now inside of the function, within the bracket. And those transformations, I'm just going to write out the general equation again. The k and the c are the x values transformations. We are going to talk about the k a little bit more in detail in a minute because that is a new transformation for the grade 11 course, but the c transformation you have seen before. And this is what I was talking about as to, like, would you be able to choose the correct x values to plot this point, these points, knowing that the graph is now going to be moving to in a horizontal direction. In this case, we know from last year and our transformations of quadratics that when you have a +1 in the parentheses, it actually means that your graph is going to be moving to the left by 1. So you would need to know that to choose the correct x values. So let's say you didn't know the negative 14 to 13. You were given an equation, how would you pick those x values? And this is the problem with that technique is you would have to kind of know, well, where are the original x values on my graph from the equation? And what are the new ones that I'm going to use going to look like so that I get relatively nice points to graph? By using the transformation method, we don't have to worry about that. As long as we know our starting points, we just transform those starting points given whatever the transformation is. In this case, it's an x transformation. We just have to remember that x transformations are always the opposite of what you expect them to be. So an x plus 1 actually means move left by 1. So now all of my new values are going to move left by 1, which we can just do the calculation for. And these will give us our new coordinates. So we're going to combine these 2 points as a new coordinate, and the same thing goes for all of the others as well. So negative 15, 1, 2, 3, 4, 5, and negative 2 would bring me to here. Negative 7 would bring me to here, And you can see that all of my points are moving to the left by 1. So now that we see that, we can just use that to plot the rest of the points without actually needing the coordinates, which you sometimes won't be able to do, depending on the complexity of the transformation. That graph is now shifted to the left by 1. For this one, we would use the same idea. It is a transformation inside of a bracket, which means it's an x value transformation. A -2 means a +2 directional shift, so horizontal translation to the right. I'm just going to add 2 to all of my x values. -14 plus 2 is -12. -6 plus 2 is -4. And do the same for all the rest. And again, using these new coordinates, I can plot them, or I can just move all the points to the right by 2. Like so. So that deals with all of the translations. If we look at a slightly more complicated equation here, and again, comparing it to our general form, you need to be able to tell which of those letters is involved in the transformation, but really all that matters is, are they inside of the bracket with x, or are they outside of the function itself's parent shape or form? And the -3 and the 5 here are in the position of the A and the D in that equation. They're outside of the bracket, therefore they are y transformations. And they're just going to affect the y values. Now, we do have to follow BEDMAS at this point. The -3 is multiplying, and the +5 is adding. So the -3 effect has to come in first. So we're just going to multiply all of our y values by the A, and then we're going to add the 5. And you can do both of these transformations at the same time. In previous courses, you may have been asked to do them separately, so you can see each individual transformation, but you can combine them together all at once. And when these start to get a little bit more complicated, I'll often just use these symbols to represent that we're doing the same thing all the way through. We will do the calculation here just so that we have our new values. So -2 times -3 is -6. -6 plus 5 is -1. +3 times -3 is -9. -9 plus 5 is -4. -6 times -3 is +18. +18 plus 5 is 23. 0 times -3 is 0. 0 plus 5 is 5. And -7 times -3 is 21. 21 plus 5 is 26. Now, I may actually end up being off of my graph here because the graph is going to be stretched too much. If that's the case, we'll just estimate where those points go. And the new coordinates are generated by looking at the original x value, which didn't change, and the new y value. So -14 and -1 would be here. -6 and -4 would be here. 0 and 23 would be off of the grid by quite a bit. So it would be way up here somewhere. 6 and 5 would be here. And then 13 and 26 would also be way off the grid, above the 13 here somewhere. So our graph is going to look something like this. And what we're seeing here is the effect of the -3, which is two things. It is a reflection in the x-axis. So that means it is a vertical reflection, flipping the entire graph upside down. Plus, it is stretching it by a factor of 3, and then moving everything up by 5. So this is the overall effect of that series of transformations. Not sure if I'm making any mistakes in my calculations here. Hopefully I'm not. If I am, doesn't matter. The overall lesson is correct. Just don't make those small mathematical mistakes. I'm trying to do some of these calculations in my head, but I think I'm doing okay. So here's probably one of the most difficult style transformations. Both of these are x transformations. They're both within the function itself, within the bracket with the x values. But I'm going to write the general transformation equation again. This is helping with hopefully memorizing what this formula looks like. So we're dealing with this here inside of this bracket. And you can see that it is not in the correct format. There is another bracket, and the k is outside of that bracket. And what that requires you to do is to factor the inside of the bracket before you do anything else. If it isn't already factored, it must be factored. And this is a common factoring scenario. So we can factor out a 3 from both of those things, and our leftovers, 3 times x gives us 3x, and 3 times -2 gives us -6. Or you can think of it as a division out of the bracket. So 3 divided by 3 would be a 1 as a leftover here, and -6 divided by 3 would be -2 as a leftover there. So however you do your common factoring, now we have it in the correct format, and we can see our k value, and I'm just going to highlight that, is here, and our c value is here. Now remember that x transformations always do the opposite of what you expect. So the 3 that is multiplying actually means we're going to divide by 3. And that can cause us to have some pretty ugly x values. And unfortunately, there's no way of counteracting that. So we will potentially need to have a calculator come into play. We could use fractional values. We could absolutely use fractional values in our calculation. But we're eventually probably going to need our decimal values anyway to estimate where those points are on the graph. So we're probably just going to use a calculator to figure that out. The c value, and sorry, let me go back to the k value. The k value is a quote-unquote multiplication, which becomes a division. We still have to use BEDMAS, so that has to be done first. And then we're going to do our c value doing the opposite of what we think it is. So instead of a -2 here, it's going to be a +2. All the way down. And if we talk about what kind of transformation we can expect from k, since k is our newest transformation, if we're dividing all of our x values by 3, that means we're squishing the graph inwards along the x-axis. So this is called a horizontal compression. And that's what's new with transformations this year, is you can have horizontal compressions and horizontal stretches. So k here will be a horizontal compression, which would make me want to ask you the question, what kind of k number would we have to have there for it to be a horizontal stretch? So I'll leave that as a little bit of a challenge. So we can do some of these calculations in our head, but some of them are going to require a calculator. So using my calculator, -14, I'm going to do this off screen, divided by 3 plus 2 is giving us -2.66. running out of room here. Negative 6 divided by 3 is negative 2. Negative 2 plus 2 is 0. 0 divided by 3 is 0. 0 plus 2 is 2. 6 divided by 3 is 2. 2 plus 2 is 4. So some of these I can do in my head. 13 divided by 3 plus 2 is giving 6.33. Again, we could use fractional calculations here using common denominators to add them, but the calculator is going to give us our decimal values, which we'll probably need anyway. So negative 2.66 and negative 2. So 2.66 is almost at 3 on the negative side, and then at negative 2 for our y value would put us approximately here. 0 and 3. Oops, put that in the wrong place, sorry. 2 and negative 6. So 2 and negative 6 would put us here. 6 and 0 would put us here. And that gives us, sorry, it's supposed to be 4 and 0, my mistake. It's one thing you got to be careful with is to use the new coordinates. And sometimes it's a good idea to highlight those so that you focus right in on them, because I just made that mistake. I don't think I made it anywhere else, but it's really easy to do that. And then 6.33 and negative 7, so just past 6 and negative 7, which is a little bit further down on my graph here. Just past 6, and then 1, 2, so right about here. And as you can see, I have squished my graph quite a bit horizontally. It still has the general shape of the original graph, but it is squished horizontally and also shifted over to the right by 2, which again would have been difficult to figure out what x values to use, right? Would you have known to use negative 2.66 here, knowing that 14 was the original, or negative 14 was the original point? That's why we use the transformation method specifically, because we don't need to know that. We just need to know what the transformations are from the original table of values. So I will discuss this one with you, although it says to do it on Desmos. There's one little thing here that we need to talk about. Now, first of all, can you see that there are both y and x transformations here? The second thing is probably the most important thing to remember, along with the fact that all these transformations in the x bracket are opposite of what you expect, is that you do have to factor that before you start. Now, how do you factor a 1/2 out of a 1? And you can, because factoring is just dividing out. So you have to factor out that 1/2. So I'm just going to write that like this. What would be the leftover in the C position here? Well, how do we factor 1/2 out of 1? Well, you're dividing it out. So actually, it's a negative 1, my mistake. So off to the side here, if we do negative 1 divided by 1/2, that is what factoring is. You're dividing it out. Well, how do we divide by a fraction? You multiply by the reciprocal, and that will give us our answer of negative 2. So in the bracket here, I already had put the negative sign. We would have a +2 left over from that factoring. So anytime you have a fraction as your k value, which will happen, and remember that that means that it's the opposite of division by 2, which means multiplying by 2. For your x values, which would stretch you horizontally. And I think I had asked that question in the previous screen. So your graph will be stretched horizontally when you have a number in the k position that is between 0 and 1. And you're going to factor that out of anything that's in the C position in a case like this by dividing it out. So I'm going to leave this as a challenge for you to look up either do it on graph paper or Desmos. But I would suggest you do the table of values transformations to see if you get the same answers that you would on Desmos for this one. So that's the end of that lesson. We will talk to you soon.